So today's talks are pretty much geology and biology, chemistry-esque related. But I've been tasked with giving you a bit of an introduction to geology. I will give you a disclaimer. I have a degree in biochemistry, and I've only been doing geology for about a year and a half. I'll do my best. But so those of you who haven't met me already, my name is Jess. I'm one of the organizers. My talk today is geology and biology, putting the ology in astrobiology. So hopefully you guys watched my video, got a bit of an intro to stuff. So just, yeah, Jared? That's really, thanks. Feel free to ask me any questions. If you guys have any questions, you don't know what I'm talking about, throw a hand up. This is supposed to be kind of an informal warm-up thing. So what I'm going to talk about a little bit is start off with an intro into the geologic record, a little bit about early Earth and Mars, introduce the idea of life, what are habitable paleo environments, where we would find those in the geologic record on Earth and Mars, and what evidence for life we see in the geologic record, and then talk a little bit about analogs. So I'm going to do my best to try and touch on what everyone today is talking about, at least using a word or two from their abstract, if not more. So geologic histories. So geologic time, for those of you that aren't started, 4.5 billion years ago, whenever we had the Big Bang. Earth and Mars started about the same, and now here we are. Earth is green, abundant life. Mars is kind of a polar desert. But why do we care about this? Well, understanding geologic context is really important in the realm of astrobiology because it provides constraints for depositional environments. If you know what the geologic context of an area is, you can know how those rocks were deposited there, which tells you what the paleo-environmental conditions were. And this basically constrains habitability and whether or not life could be there. And the geologic context also constrains whether or not you'll have biosignatures preserved. We heard about this a little bit last night, how sediments are better than, say, volcanics for preserving. So if we understand that, we can really kind of tailor our search for life in the universe and where we should be looking for evidence of life. So in the beginning, we had planetesimals like this, flying around, hot, burning balls of molten rock. And they went through the process of planetary differentiation, or at least the terrestrial planets did. So this is a process in which denser materials separates from less dense materials. So for Earth, we have an iron-nickel core. All the heavy iron, nickel, heavy elements sunk to the core. We have a lighter mantle, which are iron and magnesium silicate minerals, and then a lighter crust, which are mostly aluminum, potassium, sodium silicates. So this is Earth and Mars now. Earth, you can see, iron-nickel core. You've got your liquid outer core mantle, your crust. Mars is also similarly differentiated. You've got a core mantle, although you can see, based on the redness, that it's not as warm on the inside anymore. So what's going on when we talk about geologic processes? Well, right now, this is Earth and Mars today. Are they geologically active or yeah? I think deep down, yes, but there's no large-scale mantle convection like Earth has right now.
As soon as we have a seismometer there,
yeah,
we'll have a much better.
That'd be great. We could get one. So we're talking about geologic processes right now. Impacts are the most ubiquitous process in the solar system. Earth and Mars are both still subject to impacts, although on long geologic timescales. Volcanism, Earth definitely has volcanism now. Mars did, not so much anymore. Plate tectonics, we'll hear a lot about this later today. Earth, definitely yes. Mars, not really. Chemical weathering is still happening pretty much everywhere. You've got redox reactions to that happening. Biological weathering, Earth, yes. Mars, not so much. And wind and water erosion, Earth, definitely. Mars, minimal. We see evidence for water erosion going on now, not a whole lot. Wind erosion, the atmosphere is a lot less dense than it is here. There's a less wind erosion going on. So basically, Earth is geologically active on billion-year timescales. Mars is kind of geologically dead right now, if you want to call it that. So let's talk about Earth's early geologic history. So this is a Hadean, or what the Hadean was believed to be like in the 50s, kind of a hellish type place. But now we have a more, I guess, mellow view of what the Hadean was like. This is the more cool and clement updated reconstruction. So this is based on 4.4 billion-year-old zircons that were found. Zircons are very, very resistant minerals. They're resistant to weathering. And so these were dated using uranium-lead dating. And They were found in 3.1 billion-year-old metasediments. And why these tell us that Hadean Earth might have been cooler and more clement is that these zircons are similar to zircons we find in granitic rocks, modern granitic rocks. And this tells us that we had subduction of hydrated basalt in subduction zones. And this tells us there must have been water on the surface. So there was some water there. As well, the oxygen isotope fractionation in these zircons indicates that they were formed at low temperatures, so not necessarily a molten ball of rock. When we talk about early Earth, or the Archean from 3.8 to 2.5 billion years ago, this is a photo you guys are all pretty familiar with. We had a higher heat flow, so the mantle was a lot hotter. The planet hadn't cooled as much. We had plate tectonics, although some people don't agree that we necessarily had plate tectonics in the Archean. I think Lena's going to touch on this a little bit. We had abundant volcanism because we had a hotter mantle. But we had a developed hydrosphere and atmosphere. And this isn't debated anymore, not like, for instance, in the Hadean. But we also had increased weathering and tidal cycles. So what does the Archean rock record tell us? Well, Archean rocks, don't worry too much about the details of this. It's a lot of geology jargon. But basically, what's preserved is primarily basalt, so volcanic rock. These are lava that's been extruded and is hardened into basalt. But we also have a special kind of volcanic rock called a komatiite, which erupts at a much higher temperature than basalts now. So we don't see those anywhere in the rock record except for the Archean, because the mantle wasn't hot enough. So they have a higher eruption temperature and a higher magnesium content. And most of the rocks that we see preserved in the Archean are from regions like this, so subduction zones, where you have subduction of an oceanic plate, melting, lots of volcanism, a lot of it's seafloor volcanism. So what do we know about the Archean atmosphere? Well, we basically have no direct measure of the Archean atmosphere. We don't necessarily have air pockets in rocks that we can measure. But minerals are great at recording past paleoenvironmental conditions. So we have geochemical proxies we can use. So redox-sensitive elements like iron that will tell us a little bit about the atmospheric conditions. So we know that it was anoxic, high CO2, lots of methane, some NH3. So a lot of this is from, there's tons of volcanisms. We've got lots of volcanic degassing, spewing this stuff into the atmosphere. And somewhere around 2.5, we have this big bump in oxygen in the atmosphere. So this is the GOE, the Great Oxidation Event, which is still debated why it happened. It had to do with photosynthesis, maybe changes in volcanic outgassing. And we're going to hear more about that today as well. So what about Archean oceans? Archean oceans are really interesting from an astrobiological perspective. We know they were anoxic and acidic. They had high dissolved CO2. They're in equilibrium with the high CO2 atmosphere. But because they're anoxic and acidic, they're enriched in reduced metal species, so things like iron 2+, nickel, things that would not be soluble in today's oceans. And as the ocean became more oxygenated, they became insoluble and precipitated out. So this is one of those redox proxies we can use. We also know that it will, like the ocean now, it's salty. It's got sodium, chlorine, magnesium, and calcium salts, but abundant hydrothermal activity. I mentioned that there's a lot more volcanism, higher heat flow in the mantle. So you've got more volcanism on the seafloor as well, which means you have a lot of hydrothermal activity like this going on, black smokers. And depending what sort of proxy you use for water temperature, it's been estimated that the surface temperature of the oceans was somewhere between 50 and 70 if you believe oxygen isotopes from Church from that age. Or there's a group that did work that estimated it to be between 26 and 35 degrees Celsius, which is more closer to kind of tropical Archean ocean temperatures, or sorry, modern tropical ocean temperatures. So what I want you to get from this is that minerals constrain the environmental conditions. So if we can take, we know the stability fields of a certain set of minerals, and we can look at the rock and find it. If those minerals are there, we can place them in the stability field and make inferences about what, for instance, the hydrogen, H2, so the acidity, and the CO2 content of the atmosphere and the aquatic environment in that time period were. So this is what we know about Earth's early geologic history. Basically, just a quick overview. We've got the Hadean, core formation, differentiation. This is where we see these early detrital zircons, which tell us that it was not actually as hellish as we thought it was. It was more cool and clement. With the oldest rocks here, there's very little rock record from this time because our Earth is so dynamic. There's a lot of plate tectonics. Things are getting recycled. But we do have the Acasta gneiss, which is here in Canada, up in the Northwest Territories, the oldest rock, while this is the oldest mineral. And then we start seeing some evidence of life somewhere in here. So let's go back to Mars. Let's look at Mars's early geologic record. Well, early Noachian Mars is very different from what we see Mars now. It was geologically active. There was tons of cratering. It was around the late heavy bombardment time. Lots of volcanism. You've got the Tharsis volcanoes, Olympus Mons starting to form, erosions, lots of valley formation, but there's still debate over whether we had a warm and wet Mars or a cold with transient water. That's still a pretty big thing in astrobiology. So when we talk about major geologic events, we had the formation of the Hellas Basin happening during Noachian Mars. We had these Tharsis volcanoes and Olympus Mons starting to kind of form and erupt. And then as we also see abundant evidence for water. This is one of the more interesting things in astrobiology. So we see several lines of evidence for water in Noachian Mars. First being morphological. So you've got evidence of stream beds, like here where MSL just found those exciting conglomerates, deltas, spring systems, alluvial fans, stuff like that. But we also have mineralogical evidence. In Noachian, it's primarily clays, so phyllosilicate minerals. And these are kind of widespread throughout Noachian terrains. And these are formed by the interaction of water with basalt. And what about Hesperian Mars? There was less volcanism, less impacts, but 30% of the surface was still resurfaced with fresh basalt. And instead of having kind of this widespread clay alteration, what you see is more sporadic sulfate alteration, which also means there was water there, but not as widespread. But there were still big geologic events going. This is Valles Marineris, which I often didn't realize how big it actually was, but when you place the US on it, it goes across the entire country. So that's a giant canyon that was formed during the Hesperian. So there were still big things happening. And now present Mars is cold and dry. It's pretty much a polar desert. Its liquid water is not stable. We heard about this yesterday. Its surface conditions are below the triple point of liquid water. You've got incredibly high UV flux because there's basically no atmosphere. It's really oxidizing. There's no liquid, but there is maybe some ice up in the poles or subsurface ice. So here we have just an overview. Early Noachian Mars, you've got clay alteration, fluids. You've got sulfate alteration in the kind of Hesperian. And then from the Amazonian on, it's, well, pretty dull geologically. So I'm just going to talk about life quickly. I'm not going to go too big into it. Could talk for hours about the definition of life, what life really is, but for now I'm just going to stick with a NASA working definition. Life is a self-sustained chemical system capable of Darwinian evolution. Good enough for us today. So what does life require? Well, firstly, life as we know it. So us. We require liquid water, the bioessential elements, so carbon, hydrogen, oxygen, nitrogen, phosphorus, but also a thermodynamic regime capable of supporting disequilibrium. So basically, redox. If you think of life in its simplest form, it's kind of like a battery. You need the exchange of electrons and protons. It's just kind of a simple energy exchange system. So if you want to look at it from a almost like geologic, mineralogic, elemental view, this is the periodic table from the view of a microbe, or us, any sort of living organism as we know it. So you've got your bioessential elements, but you also still require some metals. You need trace metals and salts for ion exchange and to act as catalysts and enzyme for your enzymes and things like that. So, but there's some limits. So this is just kind of limits to life as we know it, because we're continually pushing those limits. Like Lyle said, he didn't think life could live below, 5 degrees, and now we're down to minus 15. So we have certain limitations to life as we know it, whether they be temperature, pH, hydrostatic pressure, water activity, metal concentration. So where in the geologic record will we look for life? Well, we need to find habitable paleoenvironments, so areas where life as we know it could potentially survive. So areas that have liquid water, the bioessential elements that we need, and then disequilibrium, so redox and pH gradients. And realistically, this is primarily in the sedimentary record. And I should note, I'm not going to discuss too much the origins of life. We are assuming that life is here. Where would it be? So when in the geologic record do we start looking for the earliest signs of life? Well, when we start seeing habitable environments, so more cool, clement, not dry, so where we have water. So somewhere in here, this area, this is where it's more interesting, because once we get beyond there, there's no doubt we know there's life there. We got fossils of fish and plants and all sorts of things. So and we're not expecting to find those things on Mars in the geologic record. So we're going to talk about this area here. We've got just kind of microbes, basically. So let's talk about habitable paleoenvironments in Earth's geologic record, so the early geologic record. So Hadean Earth. Well, like I mentioned earlier, there's basically no geologic record of Hadean Earth. We've got a couple gneisses up in Northwest Territories, but they're not sedimentary. They don't really have anything biological in them. We've got some zircons. They're not really useful either. And this is just a view from an art in 2012. It was basically a review of early Earth and life. This is, I think, a pretty optimistic view of how nice Hadean Earth might have been. But I mean, potentially, you've got some life going on down at the seafloor, some methanogenesis. But Archean Earth and the Archean rock record is what's really interesting when you're talking about early life and evidence for it. But again, like I mentioned earlier, the Earth is really dynamic. You've got plates subducting, rocks are being melted, destroyed, eroded. So even the Archean record is limited. The Archean rocks only make up 5% of the present continental crust. And most of them are volcanic in nature. So most Archean rocks are preserved in what we call greenstone belts. And this is an example of just kind of your typical greenstone belt. So it's a series of ultramafic rocks with a little bit of sediments on top. It's called greenstone because it's been basically squished and compressed and heated for 3 billion years to what we call greenstone facies, which just means that a certain pressure and temperature regime which has formed certain metamorphic minerals. So the minerals will get heated and basically they'll form new minerals, many of which are green. So things like epidote, serpentine, chlorite. So that's why they call it greenstone. But what's important here is, even though we do have a lot of Archean rock record, not a whole lot of it's sedimentary, because sedimentary rocks don't stick around as well as volcanic rocks. They tend to get eroded by glaciers. They get mostly just eroded away because they're not as competent. So when we look at early Archean Earth, so this is before we had photosynthesis, we do definitely still have habitable environments, though, especially when you talk about the high degree of volcanism and the fact that we had water. So you've got seafloor kind of areas, so maybe some methanogenesis, some chemotrophy going on here. Then you've got ocean vent systems where potentially you have life, and maybe some plankton floating around. And then if you go to late Archean Earth, where you have it's a little more habitable, let's say, we have, again, potentially terrestrial biomes that aren't necessarily ocean. You've got swamps, continental hydrothermal systems, maybe some shallow shelves where you have photosynthesis going. This is when photosynthesis and the oxygenation in the atmosphere is just starting up. You definitely have hydrothermal biomes. And I mentioned earlier, we have a CO2 methane-rich atmosphere and lots of volcanism pushing SO2, CO2, carbon gases into the atmosphere. So what do these habitable environments look like? So if you're talking about a kind of seafloor hydrothermal area here, what you'll have basically in the seafloor is biofilms like this. We have hyperthermophile biofilms and mats. So these are preserved in the sedimentary sequence sometimes, if you're lucky. And then if you're talking about black smoker type areas, you have a ton of energy there. We've got lots of reductants, lots of oxidants, water, heat, everything we need for life. And so it's actually a pretty happy place to live for, not for us obviously, but for a lot of microbes. Especially when you look back in the tree of life, a lot of microbes and stuff closer to Luca are hyperthermophiles. So in this period, this is definitely a very good place to be. And then there's also, I mentioned, later in the Archean, you've got more continental growth, you've got volcanism, and this continental volcanism, and the potential for hydrothermal kind of systems like this, where, well, they are pretty acidic or unhappy, or for us, they definitely are habitable. So this is in Iceland, a sulfur spring. But where in the rock record do we find these? Well, like I mentioned, most of the Archean rock record is volcanic. So these are a couple pictures from the Abitibi Greenstone Belt. These are what we call pillow lavas. So you can see they got these weird little pillow shape. And this is formed when you have lava extruding on the sea floor. As it comes out, it's almost like when you have a candle melting, and you've got bits melting, and it's kind of the outside's hardening a little bit, and you get these weird little shapes. So basically, as the lava hits the cold ocean water, you're getting kind of a quick glassy crystallization on the outside, and it's forming these weird pillow formations. And these are actually preserved pretty well in a lot of greenstone belts. The problem is there's not a whole lot of evidence for life in these, because I mentioned earlier, they are volcanic rocks. We also have seafloor hydrothermal systems that are preserved. So this is a VMS deposit in Brazil. This would have been formed from a black smoker system where you've got a whole sedimentary pile of sulfides. Primarily, these are preserved in mines, or you see them better in mines because a lot of Archean hydrothermal systems are really, really well mineralized, which is good from the perspective that you've got the rocks are exposed and there's a lot known about them. So this is a seafloor hydrothermal system here, and this is kind of a sub-seafloor hydrothermal system. You can see here, this black stuff up here, these are sediments. This is a graphitic argillite. That's a seafloor sediment. Then you've got volcanics, and right in here, you've got some carbonate veins. These are a sub-seafloor hydrothermal vein. So these are preserved in the rock record. And then also more sedimentary environments. So these are banded iron formations. Again, seafloor formations where you've got, they kind of record the transition from an oxidizing to reducing, or sorry, from the O2 poor to O2 rich atmosphere and oceans, where you've got, in the Archean, Fe2+ is soluble in the ocean, whereas it's not now because the ocean has too much oxygen in it. So it basically, when the oxygen levels went up on Earth, the Fe2+ precipitated out, and you end up with these banded iron formations. But again, these are 2.5 billion years old. So they've been cooked, squished. Here you can see a nice little fold, bent, and now, instead of being on the subsea floor, they're in the middle of Canada. So what about habitable paleo environments in the Martian geologic record? Well, I would argue the best place to look is in Noachian and early Hesperian sedimentary environments, because we know that the Amazonian doesn't have a whole lot of water or anything we consider necessary for life as we know it. So we do have a pretty good handle on some of these environments. They have been studied pretty extensively using orbital data, which granted is not the highest resolution, but we can still distinguish some things. We know we've got layered sulfates, carbonates, basalt, so we can put certain things in geologic context to try and make inferences about what was happening there. So examples of Martian paleo environments that might have been habitable are areas like here in Arabia Terra, where it's been proposed that these are actually remnant spring systems, where you've got kind of terraces that are formed that have been preserved. So these have evaporitic minerals like sulfates and carbonates, which have been shown on Earth to actually preserve certain biosignatures. Also, I would argue that impact environments are really important when you're thinking about possibilities for life, because they're ubiquitous, they're everywhere. But a lot of impacts, they generate a lot of heat, a lot of energy. They melt different minerals, they release certain elements, but they also, a lot of times, form post-impact hydrothermal systems. So you have a kind of a transient energy and water-rich environment in which life could have lived. Then you've got fluvial deposits. So areas like Eberswalde crater, where you've got large fluvial fans, deltas, and basins. These are definitely areas where there might have been life during the Amazonian or Hesperian. Or even more terrestrial volcanic environments, when you've got somewhere like maybe Tharsis, if you've got any sort of sedimentary kind of hydrothermal fumaroles. You don't need a ton of water to have a fumarole going. You're going to have water in the mantle lava anyways, right? So you might have areas like this, fumaroles and hot springs in volcanic environments. And then you also have more hydrothermal environments. So for instance here, this is Opportunity, I think, found this gypsum vein, which is formed by hydrothermal alteration. Gypsum's a sulfate. So definitely that could be. Or I think this is still the conglomerate that we were discussing last night that MSL found. Those are definitely could have been potentially habitable, and they're sedimentary environments where the sedimentary environment on Mars is preserved because you're not having plates subducting. It's not being eroded off by glaciers. So these are definitely potential places to look. And then, of course, Gale Crater. I haven't mentioned phyllosilicates too much yet, but they're all over Noachian Mars. And Gale Crater, where MSL right now, has a really, really well-exposed sedimentary record. You can see several layers of phyllosilicates and sulfates. And why we're so interested in phyllosilicates is, other than the fact that they're formed by water, there's also some implications for preservation of life, as well as potential for the origins of life, because phyllosilicates, like was mentioned yesterday, are almost like phylopastry. They're layers of silica tetrahedra, which could almost act as a scaffold. And they also take in all sorts of important cations, iron, magnesium, things that are required for life. So they're really interesting from the perspective of preservation of life and also origins of life. And we have a perfect opportunity to look at the Miguel crater. So what about present Mars? Well, let's be honest, right now, the present surface conditions are not so habitable. We're not likely to find anything there that we consider life as we know it, because there's high UV flux, water is unstable, it's really oxidizing, but there are still potential habitable environments on present Mars. So it's been put forward that there might actually still be some subsurface water and ice on Mars. So that's definitely subsurface. The trick is to get down there. You need a big drill. We're not going to get one on Mars anytime soon. But, I mean, it's possible. And then also looking at the poles where you've got ice, we know that there's water ice up there. You can see some evidence for it in these polygonal terrains, which are formed in the poles. You see them on Earth as well. So maybe there's some habitable environments on present Mars. And then, just to not leave anybody out, I'm not really talking about moons because we don't know a lot about the geologic record and we don't have access to the geologic record. And no one today is talking about moons. But I just threw this in there. There are habitable, potentially habitable moons, icy moons like Enceladus, Europa, even Titan with its hydrocarbon lakes. These are all potentially interesting astrobiological targets. But, so what kind of evidence do we see for life in the geologic record? And what sort of evidence for life are we looking for? Well, first, one of many lines of evidence is biomarkers, so chemical fossils. These are molecules associated with biochemical processes. So some things like complex hydrocarbons, hopanes, steranes. But it has to be something where we have constrained its synthesis. We know how it's synthesized, and we know its abundance and distribution in nature. So we have to be able to say definitively that this came from life. And we know how it went from this really complex biomolecule, was buried, heated, squished, lost some of its volatiles, and now it's turned into this. We need to be able to constrain its diagenetic record. And we also, another biomarker is isotopic fractionation. So first with organic biomarkers. These are great, but even if you find them, and you think you know that they're actually the same age as the rocks you found them in, it's incredibly hard to prove. Because these are 2.5 billion year old rocks, 2.7 billion years old. There's been lots of contamination, sampling, there's been later fluids coming through, they've been squished, heated. So I don't know if any of you follow this, but a couple years ago, Jochen Brox put out several papers saying, look, I found evidence for early life in Australia. And then a couple years later, put out another paper saying, sorry guys, I was wrong. I think it's all contamination, or not real. So that's the part. It's hard to prove that the organics are actually the same age as the rock you're taking them from, which is tricky because if we can barely prove that we have life on early Earth definitively, think about how hard it's going to be to prove that these organics, if we find them on Mars, are actually from Mars and actually from those rocks. But there are still some cases where organic biomarkers have been less disputed. So this is, for instance, the area I'm working in Timmins. These are 2.7 billion year old volcanics. And in the metasediments here, these are seafloor metasediments, they have found evidence for early life, so an early seafloor biosphere, using organic molecules, so hopanes, alkanes, and biphetanes. So on to isotopic fractionation. So we mentioned yesterday that the idea of isotopes. So an element that has two different weights. So like carbon-12 and carbon-13, same element, but just a different weight. And the fact that life exploits kinetics. Life is lazy. It basically wants to do the most thermodynamically favorable thing. So biochemical processes will cause fluctuations in the amount of different isotopes of things like carbon, sulfur, oxygen, and nitrogen that are being taken up into the being and affecting the ratio of isotopes in their environment because they're taking up preferentially one more than the other. So you measure this as a delta value. So this is basically just a comparison of your, say, for instance, C13 versus C12 compared to some arbitrary standard. So for instance, for sulfur isotope fractionation, here is bacterial sulfate reduction will fractionate. Your delta S34 will go this way, whereas just a plain mineral process with no biological input will fractionate like this. So you can differentiate between minerals that have had biological input into their formation. And so an example of an isotopic signature, one that's still pretty controversial, this is arguably the oldest isotopic biosignature we have. These are in the Issawa cherts. So cherts are sedimentary rock, and basically they have argued that they find carbon isotopic fractionation that indicates that there was life there that was affecting this. Well, they found carbonaceous material in inclusions in the chert and are arguing that it is actually biogenic based on the carbon isotope signature. Another very early Earth biosignature is sulfur isotopes in 3.45 billion-year-old stromatolites. So here they looked at pyrite and sulfur in the organics that they found in these stromatolites, and have found evidence that it was microbially mediated. And so another type of biosignature we'll look at, which are a little bit less definitive of life, are things like complex organic molecules. So PAHs, these are really interesting. They're complex, they look very convincing, but we find them in the interstellar medium. They're pretty much everywhere. So you can't really argue because they're there was life there. I mean, it means there's potential for life because you have complex organic molecules which are required for life, but we can't say definitively they were formed by life. As well as atmospheric gases. It's great if we find another planet that has a really oxygen-rich atmosphere, but we can't necessarily say that means there's forests growing all over it, right? And things like microfossils. So an example of microfossils, which are still pretty contested, is these are from the Barberton Greenstone Belt. Yep.
So sorry, what are some abiotic mechanisms for the mass generation of oxygen?
That's a good question. Maybe some weird weathering processes. If you're having oceans, what?
Hydrogen escape.
Hydrogen escape, exactly.
If you have a lot of water, you get rid of all the hydrogen, you can leave the oxygen behind.
Perfect.
Right, so the question is not necessarily whether there is oxygen, but whether the oxygen is out of thermodynamic equilibrium, right? Because you'll get oxygen in any atmosphere that has oxygen-bearing molecules in it, right? Like on Mars, there's some oxygen there, but it's in thermodynamic equilibrium with the rest of the atmosphere, whereas our oxygen is not. So you have to establish a thermodynamic disequilibrium before you be slightly more convinced that it would be a sign of life.
Exactly. Thanks, Mike. So here are some examples of microfossils. So these are actually one of the few signs for early life that are not in the sedimentary record. These are in basalts. So these are volcanic rocks. So these are pillow basalts, what I mentioned earlier, volcanics being extruded on the sea floor. They hit the cold seawater, and you basically get this kind of glassy rind on the outside. And what they found is these weird structures. They look pretty convincing, like maybe there is a microbe living there, burrowing and eating the glass. But most people don't agree on anything to do with these. So these are the Barberton Greenstone Belt, which are about 3.4 billion years old. This is in the Abitibi Greenstone Belt, which is about 2.8 to 2.5 billion years old. And these are from modern Anton Java Plateau, like seafloor glasses. So these are something that we see kind of throughout the geologic record, but not everyone is convinced that they're actually happened through biology. And stromatolites. So we're going to have a talk about stromatolites later today, but these are basically finely laminated sedimentary structures. So you get them kind of in shallow coastal environments. We see them in today's geologic record as well. But these are basically the earliest accepted evidence of life. Most people believe that stromatolites were formed with some sort of biogenic input. And these are from the 3.4 billion-year-old Strelipert chert. And then the last thing is biominerals. So these are minerals produced directly by the activities of living organisms. So our teeth, for instance, are a biomineral. They're a hydroxyapatite. Calcite shells, something like that. Or indirect precipitation of carbonates and sulfates and things like that. So on Mars, what are we looking for in terms of these types of biosignatures? Well, we've got MSL. It's drilling. It's taking cool photos of itself. And this is from Summons 2011, et al. 2011. They basically outlined the main biosignatures that they think MSL can detect and which ones would be most definitive. So the most highly definitive, they think, would be finding biogenic organic molecules. So those are those organic biomarkers I was mentioning earlier. And then biogenic gases, biofabrics, isotope compositions, biomineralization, things like that. So the things we find in early Earth are informing us on what we can look for on early Mars. So what about this idea of analogs? We're going to have some people talking about analogs later today. We've already heard a little bit yesterday about it. So analogs are basically environmental conditions found on Earth that possess physical or chemical features similar to those on other planetary bodies. We don't have access to every planetary body or environment we want to look at, so we do what we can and try and find it on Earth. And as scientists, we like to go for fact, not fiction. So we have certain parameters by which we judge what would be a suitable analog. So things like temperature, salinity, pH, pressure, UV conditions, oxidation state, water activity, and geologic antiquity. So we need to be pretty rigorous in what we consider an analog. And most analogs will not have all these conditions. We can't recreate everything, but we do the best we can. And these don't necessarily need to be places. We can also create analog environments. In a lab, for instance, we heard about environment chambers yesterday, things like that. And they don't need to be for other planets. They can be for past paleo environments. So we have analogs of early Archean Earth. So what are some Mars analogs? Well, we have analogs on Earth for basically every period in Mars's geologic history. So this is a paper by Farron et al. 2010, where they basically outlined an analog for every part of history. So for the early Noachian and whereas a colder and wetter Mars, areas like Rio Tinto in Spain, which are these acidic kind of rivers that are red and have lots of iron in them. Hesperian, which is Snowball Mars, a little bit colder. You've got, this is Axel Heiberg, which is in the high Arctic. This is where Lyle does a lot of work. And then for present-day Mars, which is pretty much a polar desert, you've got the Antarctic dry valleys and things like the Atacama Desert, Mojave. So here's a couple analogs types of analogs that will be discussed today for early Mars. So spring systems. This is a hypersaline spring system in Manitoba, where I did some work as an undergrad. Basically, you've got these silica sinters with hypersaline fluids running out all year, even when it's minus 35 in northern Manitoba, which it gets to pretty much every day in the winter. And you've got iron and sulfate and, gypsum, calcite, all sorts of evaporitic minerals. So this has been proposed in a paper we put out last year as a potential analog for Arabia Terra, those terrace spring systems. Areas like, this is a golden deposit. This is a jarosite deposit in, I think it's BC or Northwest Territories. But basically acidic iron sulfate. So jarosite has been proposed to be found on Mars. Or cold kind of Arctic spring system. So this is Color Peak, I believe, which is also in the Canadian high Arctic. So how about analogs for a present drier Mars? So this is the Mojave Desert, where Bishop et al. Put out a paper proposing these carbonates as a potential analog for Martian carbonates. Or we've got the Canadian high Arctic, where you see these kind of polygonal ice terrains, which we also see in the poles of Mars. And then I mentioned earlier we can have early Earth analogs. So my personal favorite is seafloor hydrothermal systems. And we see that on present Earth, we find them pretty much everywhere where you have some sort of volcanism on the seafloor. So this is just a map showing all the different hydrothermal systems that have been identified on on present Earth. So these are basically black smokers, which are these high temperature hydrothermal vents, and their cooler temperature counterparts, white smokers. And then also, I mentioned we have stromatolites going back in geologic time back to 3.4 billion years. We also find modern day stromatolites. These are in Pavilion Lake in BC, or microbialites, if you want to call them. So we have both of these that we can look at to try and understand what environments were like on early Earth. And then, of course, these analogs also can be used for other planets. So for instance, Europa, black smoker systems, we heard about this yesterday. You've got an interface between a rocky mantle and an ocean, and then you've got an icy crust. So you might have water-rock interactions, and hydrothermal systems on the bottom. And you also have sea ice and glaciers, which Brittany mentioned she uses as analogs for Europa. So just in conclusion, basically, the sediment's the evidence, the present that tells us the past. I don't know if you guys watched my video, but the sedimentary record tells us everything we need to know about the environments on early Earth and the history of life. So it's not just rocks for jocks. That's pretty much it, I guess.